Hello, everybody. Welcome to today's current seminar. Today we have one speaker, one talk. Our speaker is Matteo Calafà. He will be giving a talk on physics-informed holomorphic neural networks, solving 2D linear elasticity problems. Matteo Calafà is a research assistant at Aarhus University, Denmark, focusing on scientific machine learning for mechanics of material with Professor Tito Andriolo, Aarhus University, and Alan Engsti-Karup, Technical University of Denmark. He earned a double master's in mathematical engineering and computational science from Polimi, Italy, and EPFL, Switzerland in 2023, specializing in discontinuous Galerkin methods, finite element methods, and scientific machine learning. His previous projects include work in cardiac electrophysiology, ultrasound dynamics in moving fluids, and atomic clock pressure estimation. He developed the libraries DU-Beat for cardiac electrophysiology and another one for physics-informed holomorphic neural networks. With that short introduction, the floor is yours and you can begin your presentation.
So thank you very much for the welcome, and especially to all the organizers for planning this talk and giving us the opportunity to talk about our latest research. And finally, I would like to thank all the collaborators in this great project between Aarhus University and the Technical University of Denmark. So especially I'm addressed to Emil, Alan, and Tito for this great project about physics-informed holomorphic neural networks. And today I'm going to talk about how this special type of network can enhance classical physics-informed machine learning for a wide class of problems, including linear elasticity. And so, yes, I'm going to start with the application in order to give also the motivation behind this research project. And I'm going to talk about linear elasticity, which is a very well-known, quite simple, but very important model to describe how solid materials deform and are stressed. So as you can also see from the figures, it's very important for practical purposes to understand the condition and the behavior of materials in terms of stress and displacements, and also, for instance, to estimate, to predict fractures, and so on. So there are many reasons and practical applications to study materials in such perspective. And linear elasticity gives its name from the underlying assumption that the relationship between stresses and strains is linear. This relationship is typically called constitutive law. And essentially, linear elasticity assumes that the constitutive law is linear. So this assumption is relatively simple, but it's still very powerful because it is very reliable in many practical situations. So this is why linear elasticity is probably the most important model in solid mechanics. And for homogeneous and isotropic materials, the linear elasticity problem can be written in terms of three vectorial equations. The first is the well-known Cauchy momentum equation, where the Cauchy stress tensor sigma is related to the vector of body forces, for instance, the mass. And this is a natural extension of the Newton's second law, essentially. The second equation is the one I mentioned before, so the constitutive law, which in this case is linear, and the linear relationship is given in terms of two parameters, mu and lambda, that are characteristic of the material itself. And finally, we need to supply a last equation, which is a relationship between strain and displacement. And essentially, it comes from the definition of infinitesimal strain tensor. It's very important so that when one solves this system, one can get all the information in terms of stresses, sigma, and displacement cu, that are the key quantities in solid mechanics. Okay, so assume two special dimensions and negligible body forces, which is essentially F equal to 0. In this case, almost magically, the linear elasticity problem can be formulated in terms of just a scalar function u. This function is typically called a stress function. And this function satisfies this biharmonic, very compact equation. And it's very powerful, very convenient in some situations, since the original system with multiple variables and multiple equations can be written very compactly in just a scalar equation. So as you can imagine, we have essentially two ways of solving the problem through the regional system, which, as I mentioned, is still a linear system, but it involves multiple equations and multiple variables. Or one can, it can be more convenient sometimes to solve the formulations in terms of a function. And in this case, the equation is just one, it's just a scalar equation, but one achieves the fourth order for the PD. So as often comes in nature, there is no free lunch, in a way that there is no alternative that is always better than the other. So one option, obviously, keeps a second order PDEs, but it involves multiple terms, and the other one instead increases the order of the PDE. So depends on the practical purpose. And finally talking about physics for neural networks, in the last few years, and I just mentioned here two works, but there are actually many others. Physics for neural networks have been employed for learning linear elasticity solutions, and through both strategies. But in the end, they managed to reach their goal of approximating the solutions, but still they are showing mild performance. And this is because computational time is still not optimal. And for instance, a finite element method is still more efficient in most cases. And also applications have been shown just for relatively simple tests. And so it seems quite challenging right now to address to more realistic problems and geometries especially. So our question is, can we do better than this? Can we at least hope to get almost real-time learning for very practical situations, for very practical problems? So this is our goal, our motivation behind this work. And this brings us to the motivation behind this H in PIHNNs. And so H stands for holomorphic, which is a definition that comes from complex analysis, so essentially pure mathematics, and is the natural extension of C1 functions to C. So essentially, holomorphic functions are complex differentiable functions. And just another term that I add to the vocabulary is entire. A function that is holomorphic everywhere will be called entire in the as follows. And I will use these terms, yes, in the next slide. And holomorphic functions, well, they are called in such a way, they are not just simply called complex differentiable, because they possess very specific, very exceptional properties. And for example, this theorem is a very well-known theorem from complex analysis. If omega is a simply connected complex set, which means that it's a set without any, essentially without any internal holes, well, a function v is harmonic, which means that the Laplacian of v is equal to 0, if and only if there exists a holomorphic function phi such that v is the real part of phi. So as you can see, this result, maybe most of you already know this result, but it's very surprising. It seems there is a very important connection between harmonic and holomorphic functions. So just to avoid any misunderstanding, this is how we basically mean with a simply connected set and what is not a simply connected set. So given this very tight relationship between harmonic and holomorphic functions, phi will be called the complex potential of V. And I think it's really worth to call it in this way. Okay, so why do we introduce holomorphic functions? Well, let's go back to linear elasticity. And just a quick mention, the previous theorem which works for harmonic functions can be almost naturally generalized to biharmonic functions. The main difference is essentially that two potentials are involved instead of one. And this is thanks to what is typically called the Goursat theorem from the French mathematician Goursat. So we mentioned the Éry-Strauss function. We said that the Éry-Strauss function must be biharmonic in order to satisfy the linear elasticity problem. And therefore, we can actually apply this complex representation to the Éry-Strauss function. And since we can automatically get stresses and displacements from the Éry-Strauss function, it means that theoretically we can get the stresses and displacements in terms of complex potentials. So in the end, if one does all the math, one can derive the so-called Kolosov-Mushkelishvili representation. So this is a very important representation in solid mechanics. It was derived many years ago. You can see also one of the original books from the 50s. And essentially, this representation tells us that sigma and u satisfy the linear elasticity problem if and only if they satisfy this representation for some holomorphic complex potentials phi and psi. So this is essentially what it's saying. Well, obviously, this representation in this form holds only for simply connected sets, but this is something that we will talk about it later. And so the Kolosov-Mushkelishvili representation can sometimes be convenient, and in the past was often used for finding some analytical solutions, because you can imagine that taking any phi and psi, you automatically obtain some solutions to the linear elasticity problem. So that's why it's sometimes very convenient. But this representation requires to, introduce this complex value framework. And also, as you can see, also from the Z in the representation, it's not a linear, it's not a linear system. So,
Matteo, I have a question. I have a question. So all the boundary conditions are used to determine phi and psi, right?
Yes, indirectly, obviously, not directly, but theoretically, yes, exactly. We didn't talk yet about boundary conditions, but we obviously need to supply these boundary conditions to the problem, and phi and psi can be indirectly determined in terms of the boundary conditions, and also the same for the Aarhus stress function, actually. Yes.
Right. So all this formulation can be done for any arbitrary boundary conditions in linear elasticity, or you're constrained to certain boundary conditions?
Yeah, for the time being, I think it's just to stay in a safe area. I think we can restrict to displacement and stress boundary conditions. Also, in the original work, they consider mostly like these boundary conditions, also boundary conditions at the infinity. But personally, I wouldn't take the risk to consider others. I wouldn't take the risk to say it holds for every boundary condition. I don't know, like usually it's for these standard choices for boundary condition, I would say yes. And probably for many others, yes.
Okay, thank you.
You're welcome.
Matteo, this is Suku here from Davis. So I had a follow-up question to what George asked. So you can impose only because typically the challenge with elasticity and neural networks is usually in imposing traction boundary conditions, the traction-free condition.
Exactly.
So based on what you have shown so far, you can impose it basically on planes that are sort of perpendicular to the coordinate axis, because in those cases, only one component of the stress is zero. So then they basically get disjointed, right? Whereas if you take if you take a plane that is inclined, then you might have a coupling of normal stresses and shear stresses.
So
zero, right? That makes it more challenging in general, right?
Yeah. So in the previous slide, I made it like a bit simple. I just said like take just two special dimensions. More formally, we should talk about plane stress and plane displacement. So essentially, when obviously solid mechanics naturally works only in 3 dimensions, so one has to make some assumptions when restricting to 2 dimensions, and one can make 2 types of options. One has basically 2 options. Either suppose that there is no, let's say, normal stress, stress that goes outside from the 2D plane. And otherwise, one can also make the option of saying, like, okay, let's assume that there are no displacements going outside from the 2D plane. And it turns out that these 2 hypotheses, which are called plane stress and plane displacement, plane stress and plane strain, mathematically, they are actually formulated very similarly, just by changing some parameters, let's say, in the formulation. So this the 2D system that I showed before is basically the same for these 2 options. One has to decide, okay, just assume that the stress does not go out from the 2D plane, or I can also choose to make this other option. It depends. So
my question was more on. My question was more not on the plane stress or plane strain approximations, but more on if you have an edge which is not, which is inclined, for example, right? And you're applying, say, tension or something on an edge which is not at an angle, basically. So on that plane, on that edge, you'll get traction-free conditions.
Okay.
So then you'll get basically the normal traction and the shear traction will involve both quantities.
Okay, now I think I got your question. Yes, in general, like when you have I called before like stress boundary conditions, but you're right. We are talking about traction boundary conditions. Well, generally we don't just restrict to the case of normal stresses. We can also obviously in general, like we generalize to any type of condition that can be applied on the border, also shear stresses. Yeah, definitely. Yeah.
Yeah,
So,
I'll let you go ahead, not to interrupt you now, but I can ask you afterwards.
Yeah. No, I'm sorry if I didn't understand the question at the beginning. Probably like I took it for granted. I'm sorry. But yes, you can impose displacements on the boundary or stress. But this stress, obviously, we don't restrict to just the stress on the normal direction. It can be in another direction, which means that there is also, in general, some shear stress that is not zero on the boundary. Yes. And actually, there are other types. We will also talk later about symmetry boundary conditions. So there are different types of boundary conditions, obviously, but most of the times are displacement or stress boundary conditions. Yes.
Yeah. Okay. Thank you.
Yeah. Welcome. So I keep now. Yes. So I was saying that this representation can be very convenient. And sorry, and thanks also for the questions. Yes. So this formulation can be very convenient because you can. So by taking any phi m psi, we can automatically obtain solutions to linear elasticity. But again, this setting is a complex value, so that sometimes doesn't help. And especially the non-linearity in the system obviously increases the level of challenge, when solving some, trying to find some analytical solution. And that's also why, presumably, numerical methods have not been really defined or for this kind of representation. And but we can come up with this idea. So can we train a physics-informed we will talk about it later. Physics-informed neural network that learns phi and psi, so the two complex potentials, instead of sigma and u. So this is our question. And we are very interested in this question because if we manage to reach this goal, well, the neural network will only have to learn from the boundary conditions since the PD is automatically satisfied. So if we really manage to reach this goal, we can get very important benefits in terms of efficiency, in terms of accuracy. So this is really what we would like to achieve. And I just draw here a picture of what would the network look like. So we get a complex input, a batch of complex coordinates Z. We employ a neural network that for now, we actually don't know exactly how to define, but we will see it later. Then we get as output the two complex potentials. And thanks to the Kolosov-Mushkelishvili representation, we automatically get displacement and stresses that solve the linear elasticity problem. And furthermore, we know that PIHNNs can deal with nonlinearity. So in principle, the obstacle that we saw before regarding the Kolosov-Mushkelishvili representation can be tackled from this perspective because PIHNNs can naturally deal with nonlinearities. PIHNNs can also be integrated with experimental data, obviously, and enable also transfer learning. But there are many other benefits that obviously most of you already know. So far so good, but we have a question now. So how to define a neural network that can generate and approximate all holomorphic functions? So we want this condition to be true, and we want to define our neural network in a way that this condition is satisfied. You can also imagine that whenever the output is not holomorphic, the whole representation will fail, and therefore all our strategy will completely give wrong solutions. So we need to be completely sure that the output is holomorphic and that our neural network will approximate all holomorphic functions. So this is our goal. And so that's why we address to the new challenge of shaping our holomorphic neural network, so PIHNN. And we start from a very simple consideration. Sums, products, and combinations of entire functions are entire. And this is a classical result from complex analysis. So despite this might be quite simple, it's actually very important for us because it tells us that multi-layer perceptions with entire activation functions are also entire. So this is a very good news. It means that we have at least one option for our neural network to be holomorphic. And I just recall entire means holomorphic everywhere, just as a recall. And now we need to address to the second question, so we have at least one option for the neural network to be holomorphic, but can this network approximate all holomorphic functions? So in other words, do we have any universal approximation property for our network? And this is something that we proved in our work. Essentially, if phi is an entire function that is not a polynomial, and D obviously is a simply connected set, then a network defined as previously, well, it will satisfy the universal approximation property compacted on the space of holomorphic functions. So this is very good news. Obviously, I will not talk about the details of this proof. It's quite technical, but to sum up, this option, this choice for our neural network will be holomorphic and will approximate all holomorphic functions with desired accuracy. So this is exactly what we were looking for. And so it is worth to try to follow this path and see where we go. Yeah. So next task is to choose our activation function. We start really shaping our network. So the next question is, okay, we know that our activation function must be entire and cannot be a polynomial. How many choices do we have? Actually, we don't have many options, unfortunately. We have the cosinus function, we have the sinus, the complex sinus, and the complex exponential. We have obviously also the combinations of these three, but we don't have actually many other options. And just give you an example, just trying to motivate you on this statement. Well, you probably all know about the sigmoid function, which is widely used for classical networks, because as you can see also from the plot, it's smooth, it's monotonic, it's bounded. So it has all the best properties for the activation functions. So why might think about extending the sigmoid function to the complex field? And so we define the complex sigmoid as written here. But what about if we evaluate this function at z equal I pi? Well, it's easy to realize that we get a singularity. And it's not only that, actually we have infinitely many singularities, and the complex sigmoid will look like that. So it's a terrible function. And so I remark again that actually we don't have many options for the activation function. The message I want to give you is that generally when one extends from real valued networks to complex valued networks, one needs to be a bit careful. And especially for holomorphic neural networks, where there are some very important restrictions and conditions that need to be satisfied. And obviously, nothing has to be taken for granted, because some results that are apparently true in the real case, maybe they are not true in the complex case. Just give another example. You probably know about batch normalization, which is a very well-known and widespread technique that is used for classical networks in order to improve the performance of the network before the training. Well, this operation cannot be applied to our case because it's not holomorphic transformation. Essentially, the batch normalization involves the variance. The variance is a function of the conjugate of the input, the complex conjugate. And the complex conjugate, obviously, leads to a transformation that is not holomorphic. So this is another thing that cannot be used. So unfortunately, there are many restrictions. And just as a final remark, we just noticed that cosinus, sinus, and exponential in the complex field, they have actually very similar properties. And just to recall the Euler's formula, so that the exponential is essentially a combination of a cosinus and a sinus. So just that one shouldn't make the mistake of thinking that the sinus is better than exponential because the exponential have exponential growth and the sinus doesn't have. They actually have the same properties. So the sinus has the same exponential growth, it's just in another direction, but it has. So it's very important also not to make these simple mistakes. So before choosing our official activation function, we will talk about weight initialization. And the reason is the following. Common strategies that you probably use at least once in your life, like Xavier and Hey weight initialization, are essentially not suitable for our purpose. And the reason is that, okay, our network is complex valued, but that's not the main reason. The main reason is that these weight initialization strategies make some assumptions on the activation functions. These assumptions are clearly not satisfied by our activation functions that have exponential growth. And therefore, we need to define, propose, and employ our specific ad hoc weight initialization for our holomorphic neural networks. So this is something that is very important for employing these networks that are deep enough. Otherwise, we can just employ small networks, but we want to apply to also realistic problems from solid mechanics, for instance. So we need this strategy in order to develop deep holomorphic neural networks. And obviously, the derivation was a bit technical, if you can also see from the paper. But I just give the main highlights. Essentially, we need to find a criterion to define our weight initialization. And we start from the hypothesis that we want to impose some stability of the variance in the forward and the backward paths. So this criterion is actually quite standard. It's also a criterion that was used in Xavier and Hay initialization. Essentially, in the forward path, one takes an input as a batch from a normal Gaussian distribution of unitary variance and sees how this variance propagates across the layers in the forward path. And wants to impose that this variance keeps almost the same, because it doesn't want to have exploding values or vanishing values. And similarly, one wants to impose a similar criterion in the backward path when there is the backpropagation. The main difference is that here, it's not simply the evaluation of the network, but it's the evaluation of the gradient of the loss function due to the backpropagation for the optimization step. And therefore, one assesses the stability of the variance related to the first order derivatives of the loss function in the backward path. The main difference in our case is that obviously different activation functions will lead to different results, as I mentioned. But also we want to address not to just the first derivative, but to all derivatives until order n+1, where n is the order of the PDE. The reason is as follows. When one evaluates the backpropagation, so one has to evaluate the first order derivatives of the loss function. But the loss function is in general a function of all derivatives until order n. And therefore, in the end, we get something that combines together many derivatives until order n+1. So this is also another important step that we wanted to supply to our criterion. And obviously, calculations and mathematics become quite challenging, but we restrict to this choice for our activation function. We restrict to exponential activation function. And this allows to greatly simplify some terms and make some mathematics that is still, that can still be arranged in some way. And the final result is this weight initialization, again, restricted to the exponential activation function. And obviously, this weight initialization strategy looks a bit more involved than Xavier and Hay weight initialization, but it's what is really, it was a very important step in our work to develop and to employ these networks, because as I mentioned at the beginning, is exactly this weight initialization that allows our network to fully reconstruct solutions also to challenging problems, thanks to the ability also to develop stacked and deep layers. And that's thanks to this important step in our work. So we talk about all the main challenges related to the construction and the shape of this network. So it's time to see what we defined so far. Well, as before, we consider a complex input, so a batch of complex coordinates. And notice that now we employ two different independent branches because we want to learn the two complex potentials independently. Each branch is a multi-layer perception with exponential activation function. So that we know for sure we can exploit the previous properties. We know that the output will be holomorphic. We know that we can approximate all holomorphic functions. And in addition to that, we can also apply our smart and ad hoc weight initialization for this type of network. We can apply automatic differentiation and we can compute the derivatives of the potentials. And we notice that we compute actually up to second derivatives, which is good because it's the same order of the original PDE. And it's not like 4 as for this A restretch function. So it's still like doable, it's still reasonable. And then we apply the Kolosov-Mushkelis video representation. And finally, we can get our loss. And here, okay, we just focus on data from the model and not experimental data. But again, this loss is just in terms of the boundary conditions, the residuals of the boundary condition. And I want to remark this again, because this was exactly our original goal, our initial goal, not to learn from the PD because the PD is automatically satisfied. We just learn for the boundary conditions. And then the rest is actually quite standard. We compute the gradient of the loss function thanks to backpropagation, and then we optimize the weight. Just some two final remarks. the complex derivative is computed in some libraries like PyTorch as a combination of real-valued derivatives. And this is thanks to what is called the Wirtinger calculus. And you can search on internet everywhere, is something that's well known. But just to mention that the complex derivative is computed in a very specific way. It's not obviously as the real-valued derivative. And instead, the optimizer works exactly as in the real case, since the loss function has real input, but is as complex input, but as real is real valued. So in the end, we employ the Adam optimizer, and it works exactly as in the real case, in the standard case. Okay, so it's time to assess our strategy, and we consider a relatively simple test with a plate, and we have traction. So this is normal traction, but in general, it is not. So traction on the two sides. And we focus on just the first quarter on the top left. And indeed, on the dotted lines, we apply some symmetry conditions, since we know that this problem is symmetric. So I wanted to depict here the distribution of the training and the test points, since, first of all, it's very important to remark again that we just learn from the boundary conditions. We don't have training points in the interior of the domain. And also to focus on, actually, these training and test points are not that many, just a few hundreds. So this also is something that will enhance the efficiency of the method. And we show our first contour plots. In the first column, we get solutions of the normal vertical and horizontal stresses from the finite element method, which is our, let's say, benchmark solution. In the second column, we show the solutions from our holomorphic network, so our strategy, and in the final column, we show the results from classical pins. And you can already see that our solution looks much better than the one from the classical pin. And I think it's even more clear from this table. The training time of the holomorphic approach is much shorter, as well as the number of parameters and the errors. And so all the results that obviously show a very important improvement in terms of accuracy and efficiency. So just
excuse me, Matteo.
Yes.
For the vanilla pin, which equations are you using? Are you using the same equations or the KM equations, or are you using the original equations?
Okay, so for the classical pin, we employ the original system of linear elasticity. Okay. This is something that was already developed in the library DPXDE. So this is actually, we just naturally extended, like just moved, changes some parameters in that library, and that is what we actually implemented and run. In terms of, if you want some more specification details about this, the classical pin, we employ essentially the recommended choice, which is essentially this almost the same number of training and test points. Just that for the classical pin, this number of training points is double, because it's not just on the boundary, but it's also in the interior of the domain. And yes, other options are quite standard. Yes.
Okay.
And yeah.
Also,
so,
Matteo, one more question here. So you have to use the quarter model, right? Because of symmetry, because you cannot use the entire. Otherwise, it won't be holomorphic.
Multiply connected. Yeah.
Yeah.
Exactly.
Right. So you have to use the symmetric model, right?
Yeah. But we will discuss about it later. So
use domain decomposition, I suppose.
Exactly. So we'll discuss. So very good question, because you anticipated the next slide. So yes. Also yes. Yeah. Obviously, for this problem, it was smarter to just consider one quarter. But also, this question will be addressed later. And so yes. Just as the last remark before moving to the next slide, just want to mention that the architecture of the computer, so the power, the computational power that we had. Well, basically, we wanted to stress the fact that we want something that is very quick and also very lightweight. So for these simulations, actually, just a computer with a CPU. So we didn't use actually graphic processing units. We just used a single CPU. So I guess that 31 seconds for a single CPU is still like a great result, a great achievement from in this field, I guess. And so yes, let's move on. And well, in our work, as I mentioned at the beginning, it's not just about solving things fast. but also addressing to more challenging problems that come also from practical problems and in engineering. And that's why we consider this complex geometry, which is originally from a real section. And this geometry has, well, definitely many details, but and also hybrid boundary conditions, because we have compression on the top and displacement boundary conditions on the bottom. But what makes this problem really challenging is the notch here in this area, which is essentially a concave curve, and which leads to what is typically called a stress concentration. So it's not a singularity, but it will lead to very high values in terms of stresses and displacements. And therefore, it's something that is very complex to represent, to approximate from neural networks, but also from the finite element method, actually. And so we want to test our method in this very challenging scenario. And again, we show finite element method in the first column, our strategy on the second column, and the classical neural network physics in for neural networks on the last column. So parameters and details specifications are quite similar to the previous test. And we can see that our solution is still quite able to approximate the finite element method solutions. They are quite similar, except as expected at the stress concentration. Yes, the power, the great enhancements, I think it's quite clear if the second column is compared instead with the third column, where the approximation is relatively poor. And again, you can see that the training time, the number of parameters, and the L2 errors are still giving some important claims about the enhancement with respect to classical PIHNNs.
Matteo, if you increase the number of collocation points on the boundary,
yeah,
do the results improve in this case, or?
Yes. Well, it's obviously as always a bit of a trade-off. This case, I think we employed 600 training points on the boundary, and by increasing the number of training points was not giving much better improvement. Was just an additional cost for and a longer training time, obviously. In this case, as I mentioned at the beginning, the real challenge is to represent the stress concentration. So the very high values that you can see here in the finite element method here on the stress concentration, this is the main challenge, and what makes thing very the approximation, the learning very challenging, let's say. So
I asked that because you can just put more points near the concentration point, right?
Yeah, this is a very good question. That was also our guess at the beginning, but that actually doesn't enhance the solution that much, because it's more related to really not being able to represent this stress concentration, these explosions of values. So even if you supply more trading points, it seems that the performance is very similar. It's just more expensive, obviously, because the network already knows how it should approximate the solution there. It's just that it's not able to do that.
Right. So it's more the training part, the training or the optimization, right?
Yeah, and the size of the network. So yes. This network is, I said that the parameters are almost the same, but obviously from the previous test, but obviously the size of the network, as you can see, has increased a lot, because here we need a larger network in order to be able to represent this stress concentration. Otherwise, it will be very hard, and solution will be much worse than that. Definitely, yes. That's and we will talk about it also later at the end at the conclusions.
Matteo, I have a question on this.
Sure.
Yeah, you see the displacements are actually better with the standard PIHNNs, and
yes,
only the stress is because of I guess the formula. So going back to Suku's question, if I were to use PIHNNs and use attention-based weights, I may be able to do a much better job for this problem, because I can. Do you know this? You know the version of PIHNNs with attention-based weights, either with the minimax problem or the RBA, the residual-based attention weights.
Yeah,
that will do exactly that will do a much better job here, I think.
Okay.
So the comparison is somewhat weak. Juan actually put a paper on the archives for you to see. But this is a case where if you have concentrated the stress, like this case that you highlight here, you need the flexibility to go and do some, sampling and so on.
Yeah. And it might be like we will dig into.
How do you explain that the displacements are worse here than the vanilla pin?
So unfortunately, we want also to show the displacement in this slide, but unfortunately there was not enough space. Well, actually, this just start from from a general consideration. In general, like these L2 errors are quite more like they must be considered like in a different way, because due to the fact that the stress concentration here gives some values that really explode, and actually also the evaluation of the error is not super reliable, because obviously we are comparing something that goes very close to infinity. So as like in the smooth case, the evaluation of the L2 error is in general more reliable, and again due to that, it's just because we are comparing something that goes very close to it's very high values and goes very close to infinity. And also also if you compare sigma xx and you compare which is exactly this solution and this solution, obviously this solution looks much better than this, but apparently from these L2 errors it looks like it's just like a bit lower, not that low. But the reason is what I said before, is just that most of the L2 error is in the end of the stress singularity. And for the displacements, that's a very good question. I'm also a bit surprised about that. We were surprised about that. And
Matteo, I may have missed it, but did you show the expression for the displacements in terms of the potentials? How do you get
yes,
the displacement?
I did. It's
I missed it probably.
It's true.
There it is. Okay.
Yeah.
Because I was wondering if there is something there which is probably messing up the accuracy, or the form of that is actually the stresses depend on second derivatives, right? But the displacement depends only on first derivatives, right?
Exactly. The displacement in general,
right.
So displacement in general are more smooth than in general, like in body mechanics, but mathematically it can be explained as the fact that in the stresses there is one order of derivative more. So
yeah, but I think why you're getting better stresses is that because you're satisfying the equilibrium equation exactly, right? So so that is why that is sort of that is the starting point, right? And then you can think of it as you're sort of integrating to get the displacement. I mean, in a loose sense, right?
Yeah.
That might be the reason why because it's inferred. Your displacement is sort of inferred from the potentials, right? Whereas this is more because you're exactly satisfying it. It has to be better in some sense, right? At least intuition says that, right?
Yeah, intuition says that. But also, we were actually also surprised about the displacements. Because this is yes, this is actually unfortunately I don't have the plots here. But again, you can, if you take the article for instance, you can see the plots of the displacement, and you can already see qualitatively that the displacements of the holomorphic approach look much better. And I guess it's still some tricky aspect of how the L2 error is evaluated when there are stress concentration. I think this is the reason, because again, qualitatively you can see the plots and you can be completely sure that the holomorphic approach approximates much better. So
can you
I know that
Can you also check how are the boundary conditions, how are they satisfied, how good or bad, right? The solution, right?
We did it. Unfortunately I didn't put it into this presentation, but also if you pick the article, you can see that in the third test we evaluate the boundary conditions, since also that test is quite critical, and then we evaluate how the function behaves on the boundary condition, and you can see that there is the very smooth profile of because obviously and this is also something to talk about actually, that the solutions from the holomorphic approach are solutions that are intrinsically C infinity. They are smooth because they come from holomorphic functions. So one pros is that when you plot the solution, you see that it's very smooth. You can have a good analytical properties, so that for different applications one can get some information for that. But obviously something that should be addressed and should be announced in the future is how definitely smooth approximations can lead to maybe some more difficulty in learning, for instance, stress concentrations. So this is something that obviously is a limitation of the current approach, is a limitation in general, I guess, of all methods that provide smooth outputs, so that they have good analytical properties, but maybe they can show some, it can be challenging to represent solutions that instead are not that smooth. So this is something that should be addressed. And but yes, to answer to the previous question, I know maybe my answer is not completed from all perspectives, but yes, if you really pick the article, you can and see all the plots, you can really see the difference. And yes, so I guess that these errors, especially related to displacement, have to be taken with a grain of salt or something like that. So I hope it's all good now.
Yeah, good.
Yeah. And okay, and thanks again also for the recommendation about attention-based pins. Okay, so we move on to pins on general domains. That was something that was already addressed and in the question. So unfortunately, the standard method can only work on simply connected domains, and this is due to abstract mathematical reasons rather than practical or numerical. So it's a very important and annoying restriction, because we want theoretically to extend our method to general domains, and especially in fracture mechanics, often one has to consider holes in the material, so and not only in fracture mechanics. So it's very important. It's very a necessity for us to extend to general domains. And as it was anticipated, we think about the domain decomposition strategy, which is something that's connected to the pins, was something developed in 2020, proposed in 2020 as XPin. And obviously one can take as all subdomains to be simply connected. So the idea is as follows. For simplicity, obviously we consider just two subdomains. And if we consider a not simply connected domain as a donut, we split the domain into two subdomains, left or right. We employ two independent networks, one that solves the problem on the left and one that solves the problem on the right. So these networks are theoretically independent. They solve the problem independently, but also we want them to communicate. So therefore, we want to make them communicate through the interfaces, which are essentially the borders between the two subdomains. And there are some specific properties and equations that are applied on the interfaces. For linear elasticity, this is relatively simple, since one has to apply these conditions. The discontinuity of the displacement must be equal to 0, and the discontinuity of the normal stress must be equal to 0. And so this can be simply supplied. So as a recap, we employ two independent neural networks, but in the loss function, we sum up together the residuals of the boundary conditions from the left, the residuals of the boundary condition on the right, and plus the residual of these interfaces conditions. This is simply like the idea, essentially the idea. And so we can show like a final test, and we consider the same problem as before, just also because maybe it's interesting to compare with previous tests and previous results. This time we instead consider the whole domain split into four subdomains, so there are also 4 interfaces gamma. And again, from the contour plot, everything seems okay. And again, from the table, it's clear that training time number of parameters and the relative L2 error, they are in this case are of the order of 10, a ratio of 10 from classical pin to holomorphic pins. So yes. So
I had a small question, Matteo. This is Varun from Brown. So I was just trying to understand if the method is still applicable when the loading is not symmetric, like on both sides. Yeah.
So yes, this is obviously this test looks quite simple because it's all symmetric. But in general, like obviously, the method works with any domain. I can also be not symmetric, obviously. We decided to show this test because it was just interesting to see the comparison with the previous one. But obviously it can extend to all. It's not. Also, unfortunately, also to connect to the question at the beginning, we have also seen just fractions normal to the border, but actually it also in general for general fractions. So yes, it extends to general domains, and especially with domain decomposition also to multiply connected domains. So this is good news.
So I could have different loading on each side and it still works, right? Okay.
Yeah. But if you mean body forces, that's not true. Like at the beginning for the area stress function formulation, we assume that the body negligible body forces. So if with loading you mean body forces, no. But if you mean asymmetric boundary condition, that's true.
Yeah, just the boundary conditions. Okay.
Yeah. Okay. Perfect.
Thanks.
And so for our conclusions, yes, physics in holomorphic neural networks. Well, they represent an innovative strategy to substantially enhance physics for machine learning for class of problems, for the class of problems that can be stated in terms of holomorphic functions. So as I mentioned before, I think the two main limitations are the following. First of all, is that this can be applied only to a certain class of problems, obviously not to all problems in nature. And the second limitation that I discussed before is that as a smooth approach, there are some challenges when one has to approximate definitely not smooth, not regular solutions. But in contrast, we have many benefits. And well, first of all, the incredible speed up on the training time, and this is due to the fact that the PD is automatically satisfied, and one only needs to satisfy the boundary conditions. And then there is an important reduction in terms of memory, and this is due to both the training points that again I show again this picture where I think it's clear that we are just training on just a bunch of training points, but also there is important reduction also in terms of the weights of the neural network. The neural network is generally smaller, much smaller, and this saves a lot of memory. And then something that we didn't mention before is the smoothness of the solution. Well, as a benefit, obviously, since one can get some analytical properties and analytical, for some practical reasons, one can maybe decide to have a smooth solution. And then we have an important reduction in the number of hyperparameters, since the loss function is composed by the residuals of the boundary conditions. So there is not, for instance, the residual of the PD. So this allows to reduce the number of hyperparameters. And finally, the output of the neural network is available in both real and complex representations. So from the complex representation, we know that it's quite easy to get the real representation, but it's not true the opposite. And it can be useful for some practical applications to get both representations. For instance, in linear elasticity, the complex potentials give a lot of information regarding the solution and the stress field. So yes, that's all for me. And you can, first of all, I thank you very much for the attention. I hope you enjoyed and it was interesting for you. You can check out the article we just published on CMAM. And well, on the left, you can scan the paper. And also we provide an open source library. So it's a repository on GitHub, and where we provide all the tests that have been presented here, but also in the article and other tests. So, and maybe if you also want to give your support, and you can check it out and give your view on that and your help. Thanks very much. And thanks also again to all the organizers. And yes, so if you have further questions, I'm here to answer.
Thank you so much, Matthew, for your great talk. Now we open the floor for more questions. Do we have any other questions for the speaker? Yes.
Hi.
Yes. Can you introduce yourself
This is Kyle. I'm a student here in the Toronto group. So I wonder, instead of using this really good holomorphic pain, is it possible to approximate holomorphic functions by using the real valued plane for its real part and imaginary part, and then impose the Cauchy-Riemann equations, for example. Would that be something that is possible to do?
So theoretically, it's possible. Yes, thanks for the question. So one can definitely employ like a complex value, a standard CV. It's called CVNN, complex value neural network. So this is a standard complex value network, and then applying also the Cauchy-Riemann equation. That's true. But obviously, in such a way, one doesn't get all the benefits from the holomorphic approach, because obviously one has to train again on the interior of the domain. So I guess it's it's an alternative solution, but then you don't get the same benefits that you will get from a completely fully holomorphic approach. But that is true. In general, like complex value neural networks are defined in a way that they can approximate all continuous complex functions. So they're not restricted to holomorphic functions. And so, yes, it's possible, yes.
Thank you. Yeah, do we have any other questions?
Yeah, Matteo, I had a question again.
Yes.
So the question is that in 3 dimensions, right, you have these Maxwell stress functions, Maxwell stress tensor rather, which are the analog of the Airy stress function. So I was wondering, is there a counterpart of that? For that, is there a holomorphic counterpart of that?
Yeah. So there is some research going on. Obviously, the whole work from Muschelishvili is the one that is definitely most important, and almost everybody in the field of solid mechanics knows about it. But also in the latest year, they proposed the quaternions as a way to represent the linear elasticity in 3 dimensions. And this is something that is quite, I mean, it's just at the beginning. There are just a few work on that, but it's something that potentially can be applied for sure. But the analysis becomes very complex, also complicated. Also, just to mention, for our universal approximation property for holomorphic functions, that was not to be taken for granted. I mean, we proved that, but we didn't know if it was right or not. So I can imagine that if one wants to explore the 3D, well, there is a lot of work to do in that direction. That is for sure.
Well, the expressions for the Maxwell stress tensor is very similar. It reduces to Airy stress function with only one unknown, but then you have 3 of them. This is like a diagonal tensor. So them and the relationships are kind of similar, right? I mean, analog.
Yeah, I didn't know about the Maxwell Cauchy Maxwell stress function.
Yeah, the Wikipedia. It will be on Wikipedia.
Yeah,
if I find it, I'll post it if I find it. Yeah. So
yeah,
because
then find about quaternions, that is for sure.
Yeah,
and also that
because then you can, if there is a holomorphic counterpart of that, then that could be in 3 dimensions, because then you only need to figure out surfaces. You need to have collocation points only on surfaces, right?
Yeah, logically,
yes. It's like a boundary element kind of analog, right? Where it makes it much more attractive, of course, right?
Yeah, exactly.
3D is much more difficult than 2D, of course. So that's why.
Yeah, and I also guess that since in 3D quaternions need to be employed, there is maybe, I'm not sure, intuitively maybe there is a decreased efficiency, because like a 4th dimensional space they used for a 3-dimensional space, whereas a complex space of 2 dimensions they use for 2 dimensions space. So I don't know. There is much to do in this direction yet.
Yeah, I found a Wikipedia link. I'll just post it if you are interested, right? It's on stress function.
Thanks a lot. Thanks a lot, and thanks also for very interesting questions.
I wanted to thank Matteo for a great talk, but also I want to thank Alan, who recommended. Alan from Denmark. He's I saw him somewhere in the audience, who I think recommended this talk. So this is a great talk because it had a little bit of math, a little bit of benchmarking, a lot of creativity, which is great.
Yeah, thanks a lot. Yeah.
Yeah.
Thanks for all the compliments.
Okay. Do we have any other questions?
Yeah, I have one. Oh, okay. Can you mute? Hi. So I'm Nikhil. I'm a PhD student at Crunch Group. I have one question. So does your method would work with like kind of an inverse problem where I want to, let's identify the material property or like parameter identification in that case? Because I see it has to go to the phi and like the potentials, right? So do you think it will be extended in that case?
I don't hear you very well, actually. Can you maybe speak a bit closer? Or
yeah, so hi, can you hear me now?
Yeah, a bit better, yeah.
Okay, so my question was, does your method could be extended to the cases where I want to identify the material parameter, let's say elasticity modulus or something? In that case, it could be useful.
Let me think about it. Yes, theoretically, yes. Let's go back to the Holomorphic Neural representation, if it doesn't bother you. Okay, so this gamma is the colors of constants, which can be obtained from mu and lambda. So essentially, in solid mechanics, there are always two coefficients where you can get the other couple of coefficients and so on. So I guess that theoretically something that can be done, like directly in the Kolosov-Mushkelishvili representation. There are the two material parameters. Yes, why not?
I see.
We actually, as we said, it's something completely in another direction with respect to the classical PIN approach. So again, there is so much that we can potentially explore. So obviously, we didn't have time to think about all the possible directions that one can take, But I guess so, yes. Yeah, sure.
I see. Thank you. And I have one more question. So does your method, solution from your method satisfy the positivity of Jacobian by construction? Because I am assuming that you satisfy the PD by construction, right? So you have the determinant of deformation gradient would be positive in your case, like always.
Okay, what do you mean exactly? Maybe I don't get you.
So you have a determinant of deformation gradient, right? So determinant of F, which has to be positive at all the points, right, interiorly.
Yeah.
So I'm wondering whether it's satisfied because you satisfy the PD, it's already satisfied by construction, because that could be and that's usually it doesn't appear in the constraints when we regularize the network, right?
Yeah, I guess so. Like I admit that I'm not that expert in the subject you're talking about. I don't know if maybe Tito and Alan can answer to
yes,
this.
I can answer. Yes, it is. It is satisfied by default, basically.
I see. Great. Thank you.
Yeah, that's a great property. Good question. Yeah.
I saw Raj may have a question.
Yeah, thanks. Thanks, Matteo. Very excellent talk. And I just had one question. You mentioned that sigmoid activation function will not work for this case. So did you try the complex version of sigmoid or any transcendental function? Because we did a project on the Maxwell's equation for this complex solution, and transcendental activation function worked very well. There is a paper on that, backpropagation with transcendental activation function. So I think that can rectify the issue of what we have with sigmoid function. So
let's go back to the discussion about the complex sigmoid. So
yeah.
Okay, the discussion regarding the activation function is very wide in general. It's there is a lot to say about that. Actually, just present like an example, but you can also see nowadays there's also many articles about possible activation functions for general complex value networks. There is still a lot of discussion about that. Apparently, there was a work for 2023 that just said no, it's not like that. The real answer is this. So there is still something working on. And if your question is like, did you try this? You asked like if we tried this activation function, and the answer is yes. When we really started at the real beginning of the work, we could imagine all this stuff, obviously. And at the beginning, obviously, the results were very disappointing, let's say. The point is that, okay, there are two main problems when one adopts an activation function like that. First of all, this activation function has some singularities. So if you put this activation function, the solution you get has some singularities, and it's not what you want to get. I mean, it's not your solution. But that's not the main problem. The main problem is the following. If you allow a general activation function to be used, this means that the output of your neural network is in general not holomorphic. So this is what it's saying. It's saying like you are like making the you're making the possible outputs, the set of the possible outputs larger, and then your neural network will learn the problem by searching for other functions that are not exactly what you're looking for. So the first thing you say is that the loss function goes to zero, like immediately, very quickly, but it's just because it's not going in the right direction, is trying to find a solution that is not actually a solution. So this is what happens, essentially. So you see that there is the right restriction, the right definition of the problem, the right implementation of the network, if you really see that the network goes down, but not too fast, because obviously there is something, otherwise there is something that is wrong. And usually it's because, as I said, you, by mistake, you move from the holomorphic output to an output that has a general form, has a general definition, and therefore, you know, it's like you just have to solve a problem just with the boundary conditions and not with the PD. So it's a trivial solution that is not actually what you want to get.
Yeah, that's correct. And last question, and the performance of the pin you showed, that is for strong form, not for weak form, right?
Yeah, yeah.
Okay, thanks.
I mean,
yeah, I think a weak form might reduce some complexity. That is what I was inferring to. So it might be much more faster than what you have in the strong form, because most of the cost comes from AD. So
comes from, sorry, comes from
due to
automatic
the
differentiation.
Okay.
In the weak form, you reduce that, right? You change the first order, second order becomes first order. So
I'm not sure. Like I got what
we have Matteo. We have a paper called HP pin.
Yeah.
The HP finite element.
Yeah.
So that's basically the formulation. And so you integrate by parts, you only have first derivatives, or actually can take twice by parts you can have.
Okay. Yeah, I agree on that. Yeah. And
but you have to compute the quadrature, so it's a little.
Yeah. No. Okay. Yes. I know what you mean now. Sorry. But how to say is like the holomorphic approach obviously relies on the strong form and not on the weak form. So it's I think it's like you should change the entire philosophy of the work. It's not just
no. I was inferring the baseline which you consider for comparing the cost, actually the pin, the vanilla pin you use. So I was inferring for that model, like whether you use strong form or weak form. So that's why you use strong form.
Yeah. Okay. Sorry.
Matteo, on that point and about the concentration that you had the very nice round, did you do the L-shape problem that everybody does that has a singularity? Because then you don't have continuous functions. I mean, you have C0.
Oh, the L-shape. Now I know what you mean. Yeah. We didn't try that test, to be honest. We went straight.
The stress is what is it? Suku will remember.
Yeah. The stresses are singular.
Stresses are singular because it's R to the 2/3.
Yeah, it's 2/3.
It's 270 2/3. Yeah. So take derivative. It's 1/3, 1/1/3 of R. 1/R to the 1/3.
Yeah. And no, actually, we didn't. I know the test you are talking about, and I mean, we tested on different geometries, different, but not that one, to be honest. I don't know.
Standard benchmark, the L shape.
Yeah. We should. That's a very good input from you. So it's something that we can definitely do. Yeah.
Matteo, I was thinking of something we have not touched upon. One is that, the problem, the way you're solving it, right? I mean, do you know that the numerical solution is it well posed by itself? Because, basically any function is going to be satisfying the equilibrium equations, right? Which you get output. But then, I mean, can there be multiple solutions or multiple representations that can satisfy, because you only satisfying the traction or the displacement at discrete points? So there could be different representations, right, which can deliver similar approximations, right?
Okay, yeah.
Similar accuracy.
So, yeah. So
you're not looking for you're not looking for a magic function, right? Though they might exist, I'm not sure, but.
Yeah. So I think I can split the answer into two parts. First of all, the well-posedness in this case is demonstrated in the work of like Mushkelishvili, but also other following works. In terms of complex potentials, like how many complex potentials give that solution, and if the solution obviously is unique, and so on. And I mean, there is a lot of things you can read about that. So to recap, to sum up the main concepts, if like a linear elasticity problem is defined as we did with, let's say, standard boundary conditions, so traction and displacement boundary conditions, maybe symmetry boundary conditions. Okay, so the problem is generally well posed, and this is from the basic theory of linear elasticity. Then, well, you also need to obviously check like how many potentials can give your result and so on. And obviously there are some quite often it happens that the potential is unique up to an additive constant or something like that, which is also something that actually happens for the displacements. If you set a problem with just traction boundary conditions, the displacements are unique up to the constant. So I think I mean, it's quite annoying, but the main thing you need to care about in this case is that comparing like displacements or comparing potentials directly, maybe sometimes it's a bit tricky because you always have to remember that they are unique up to some constants, let's say. And so this is regarding your first question. But in conclusion, we are pretty sure that in the way we set the problem, in the way also it is set in the complex framework, it's well posed, except for eventual additional constants.
Yeah, but I was thinking of if you can impose something additional, which will make it which will get rid of any constants which are lingering around, right?
This is something that we did actually in this test, in the last one, in order to be sure that we could get some. We wanted also essentially in the article in the paper, we also wanted to show the displacements, and but obviously it does like it's not so good if the displacements are unique up to a constant because it's also hard to interpret the result. So we actually supplied on I don't remember, like maybe on the bottom edge, just saying okay, here we want the displacement to be in a natural way, but just one one diagonal is enough so that you fix the vertical displacement and the horizontal displacement, and that's enough to essentially guarantee the uniqueness also of the displacement. So
because you need to remove the rigid body modes, right, in this problem.
Exactly. That's what we are talking about. Exactly. Right. And but yeah, I mean, still, I think that the meaning, the concepts, they are still like unchanged. We're just talking about solutions up to additional constants. That's what we are talking about. But regarding, I just wanted to pass to the second part of the answer, which is regarding like when we learn from a discrete set of points. Essentially, we have this property, which sometimes is good, sometimes is bad, depends on the point of view, that the solution must be smooth. So we said it's good for some analytical analysis, for some analysis of the results. It's bad because maybe this can create some problems in approximating solutions that are not regular. But in this case, it's also like a good news. It's also a good property because it means that when you have two close points, theoretically, it should know how to behave in the middle if these points are very close because it should be smooth. So that's also why I think that in many scenarios, obviously, if the real solution, the analytical solution is smooth, actually not many points are really needed. So
yeah, because I was thinking, have you solved a problem where you can manufacture like a manufactured problem, right? Where you just figure out, okay, I'm going to use this, this potentials, and okay, whatever basically solution it gives, that is what I'll impose as boundary conditions.
So
that you know the sort of exact solution, though it's artificial.
Yeah. Of course. Yeah, talking about that, I don't know if you remember at the beginning I was mentioning about the works in 2022, 2023, And there were a lot of tests where I actually had some solutions that were, I would say, relatively simple, let's say. And we didn't want to do that. We since the beginning, we wanted to find something, a strategy that can be assessed on more like definitely more realistic scenarios. Okay, this test is essentially the only exception, maybe also the one with the circular disk. But we wanted to address to not say already like this solution. I think there is no this analytical solution is not known, or maybe it's known, but in terms of series, it's already like not a manufactured solution, let's say. The only one that was known analytically and was used in the paper was in the very first test, that is the circular disk. But that was a very first test, as to check that everything was fine. And but I hope to have given you the message of this motivation and yes.
Thank you. Do we have any other questions? No, I think it's time to close the session. Thank you, Matteo, for your great talk, and thank you everybody for joining us today. I hope everybody has a great weekend ahead. Bye.
Thank you very much again to the old Crunch group, and good weekend.
Thank you.